J'invite maintenant la COP à adopter le projet de décision intitulé Accord de Paris qui figure dans le document. Je regarde la salle, je vois que la réaction est positive, je n'entends pas d'objection. L'accord de Paris pour le climat est accepté.
Paris, December 2015. The 196 countries signing the Paris Climate Agreement agree to get global warming under control well below 2 degrees centigrade by the year 2100.
If we're to achieve the ambition of the Paris Agreement, we will have to cut emissions extremely rapidly. And even if we do cut emissions extremely rapidly, that is very likely not going to be enough. We will probably go past 1.5, 2 degrees in just a few decades.
The effect that heat has on the system is something that's happening more rapidly than some of the changes we would like to make. Geoengineering is the only fast-acting approach to reduce heat directly in the climate.
Tropics are going to get very warm under continued emissions. So there could be a great demand to do something to cause the Earth to start cooling quickly.
Whether they're harnessing the excess CO2 in the atmosphere or cooling the Earth artificially, the common goal of geoengineering technologies is to slow down or even reverse the effects of global warming by deliberately intervening in the climate.
What it's meant to do is give us some time to be able to go to the energy mix that we need, and in the meantime, to limit the damage.
La geoingeniería viene como una excusa perfecta, así, para los que no quieren hacer reducciones reales.
20 years ago, we said people need to stop putting CO2 into the atmosphere. If societies had actually gone seriously into removing CO2 from injection into the atmosphere, we probably wouldn't be talking about this now.
Coal, oil, gas. The global economy is addicted to fossil fuel energy. Far from slowing down, global emissions of carbon dioxide continue to increase. To curb the effects of global warming, scientists are now looking for ways to remove the excess CO2 present in the air.
Il y a un cycle du carbone qui est très actif sur Terre, avec un certain nombre de réservoirs, un très gros réservoir dans les océans, avec du carbone qui est dissous dans l'eau, un autre réservoir sur les continents, dans la végétation et dans les sols, et enfin du dioxyde de carbone atmosphérique. Depuis l'exploitation des énergies fossiles, on rajoute du carbone sous forme de CO2 dans l'atmosphère.
Oceans, biomass and the ground do not have the capacity to absorb the excess carbon that has accumulated in the air since the start of the Industrial Revolution. Since 1850, the concentration of CO2 in the atmosphere has risen from 280 to more than 400 parts per million.
Carbon dioxide piles up in the atmosphere. It's cumulative. It doesn't go away. Roughly half of the CO2 we put out will be there for hundreds of years. And to get it really out of the atmosphere, ocean, biosphere system will take tens of thousands, if not 100,000s of years. So we need some ways of taking carbon dioxide that already entered the environment back out. And broadly speaking, that is negative emission.
Carbon dioxide removal really gets at the root of the problem, because the problem is that too much carbon dioxide is in the atmosphere, and these carbon dioxide removal approaches basically seek to reverse our emissions and remove this carbon dioxide from the atmosphere.
According to predictions from the IPCC, the Intergovernmental Panel on Climate Change, if nothing is done to reduce CO2 emissions, their concentration levels could triple by 2100, causing temperatures to rise by more than 4 degrees.
La quasi-totalité des scénarios qui permettent de contenir le réchauffement climatique sous les 2 degrés ou sur les 1,5 degrés incorporent un certain nombre de mesures de capture du CO2 atmosphérique pour aller réduire les émissions si celles-ci augmentent un petit peu trop pendant le XXIe siècle. La manière qui est la plus habituellement utilisée dans ces modèles intégrés climat-carbone qui permettent de générer des scénarios, c'est d'utiliser la biomasse via la reforestation, la forestation pour faire des émissions négatives, donc via ce qu'on appelle le BECS.
Producing energy whilst removing CO2 from the atmosphere is what BECS promises. Plants and trees are grown to absorb CO2 by photosynthesis. They are then burnt in thermal power plants, which produce energy, and the CO2 emitted via their combustion is captured and stored away. The carbon footprint of this process is negative.
Growing trees is generally a good idea, and you're not going to find too many people arguing against you. But the issue is, can you do it at a scale which is actually going to have a material impact? The problem is that you have to grow such a huge area of these plants that it's going to have impacts on other systems in terms of biodiversity and in terms of land use tenure. So that land belongs to someone at the moment, and the issue is, well, how is it going to be affected by people using that land to take carbon away? Do it at a small scale and it probably doesn't have much of an effect, but try to do it on a scale that has a material impact on the climate, which is what this is about, and it would have a material impact on those other systems.
To remove 10 billion tonnes of CO2 per year, that's to say a quarter of all current CO2 emissions, we would need to set aside 500 million hectares of land, equal to 1/3 of all current farming land or 1/8 of the world's forests. Add to that the intensive use of fertilizers and tensions over water resources. Another method involves capturing CO2 from air using chemical processes. A researcher at the Arizona State University, Klaus Lackner, has developed a prototype that can replicate the CO2 absorption capacities of a tree leaf to a much greater degree.
Direct air capture is a set of technology to literally pull CO2 directly out of the ambient air by technical means. You can always use, and this is an alternative, photosynthesis. You could grow biomass, you can grow plants, and they collect CO2 from the air just as well. So we are calling our direct air capture artificial trees, because just like a tree, we take CO2 out of the air as the wind blows over our artificial leaves. They bind CO2.
In the mid-1990s, the physicist discovered the specific properties of a polymer that could absorb carbon dioxide. When it's dry, it absorbs the CO2 held in the air. When it's wet, it releases them back.
This is a very tiny air capture device, grams per day. And now I'm driving it into its parking spot where we can now regenerate it. And in order to do that, we have to make it wet. And so now that it reached the top, I simply let go from the pump, and now gravity drains it back. You see the water coming back and going down there. And we are simply watching this building up the CO2 level inside, and right now it has reached 1.9%, so it's going to breach 2%. So we are about 50 times higher than we are in the ambient air inside this little box, and the only thing we did is we made the resin material wet. Unlike other methods of managing the climate, this one is simply walking us back from where we shouldn't be. In other words, we dumped too much CO2 in the atmosphere, and now we are taking it back out. I think sort of from a conceptual point of view, this is the least invasive method to solving the problem.
To test out this technique, which has proved successful in laboratory tests, engineers at the Arizona State University have developed a prototype and set it up in the desert. Unlike other techniques, this device will be able to absorb CO2 without consuming too much energy.
The energy required to capture the carbon dioxide is provided by the normal movement of the wind. In other words, the wind evaporates the water off of the resin surface, leaves behind the carbon dioxide that it had carried in, and the energy of evaporation is the energy that closes that Carnot loop, if you will. So we let the wind do that for us. We harvest the wind.
How effective could these machines really be? Engineers hope to reach industrial production as quickly as possible to remove CO2 from the air.
Let's scale it up so that it's something that would fit inside of a 40-foot shipping container. A machine that size would capture roughly a ton of CO2 a day. So one of those machines would cover, in 6 days, would cover the output of an automobile for an entire year.
If we want to come down 100 ppm in 40, 50 years, that means we have to come down by 2.5 parts per million a year, which is about what we are going up right now. You would have to build 100 million such shipping containers. That's a large number. But on the other hand, it's not prohibitively large. If they last 10 years, you would need to build 10 million a year. We are building 80 million trucks and cars a year, right? So we can operate at that scale.
Inspired by this discovery, architects have now designed tree pods, artificial trees planted in the cities of the future, a project that's far from seeing the light of day.
The carbon problem is a waste management problem. I'm all for minimizing the waste we are making, moving away from fossil fuels as fast as we can, but between the time we succeeded with the transition and now, we will emit so much more CO2 that we have to, in the meantime, clean up. All the litter you generated in the past, you have to take back, because we can't leave it where it is. And that means we have to do both. We have to go to sustainable solutions and at the same time clean up after ourselves. And this is where air capture comes in the short term.
What do we do with the CO2 once it's been absorbed by these machines? 3 private companies have become involved in direct air capture. In 2010, Graziele Cicilneschi founded the company Global Thermostat, whose aim is to suck up CO2 and sell it on. It's a first step towards a carbon-neutral economy.
If you remove the CO2 and you use it commercially for drinks, beverages, like Coca-Cola, for foods, like McDonald's hamburgers that use dry ice, that is CO2, for desalinating water, which is essential for humans, for production of polymers or plastics, which are biodegradable, for biofertilizers that increase the fertility of the soil, to produce clean fuels by mixing the CO2 with hydrogen. You are removing the CO2 and you are making profits.
This direct air capture technology uses ammonia-based chemical processes. Global Thermostat has already filed 35 patents and amassed 51 million euros to develop its technology.
The same way that the Industrial Revolution led to the use of petroleum as a feedstock for the whole economy to produce energy and materials, etc., instead of using petroleum, you can use CO2. Therefore, you can have a world economy that is powered by the CO2 that we take from air. You can increase economic growth enormously while cleaning the atmosphere. And that is the revolution that is coming. That's the revolution we want to be part of.
According to a report published by the American Physical Society in 2011, the cost of direct air capture would be around $400 per ton.
The expectation is that direct air capture will be very expensive. The key issue is no one is prepared to pay for removing CO2 from the atmosphere. There's no incentive. It's as if you've got lots of different machines for cleaning the streets of rubbish, but nobody's prepared to pay you for picking up the rubbish. And ultimately, you need to have some sort of mechanism that recognizes that CO2 in the atmosphere is a waste and that we need to remove some of that waste for the benefit of society. If we don't have that, we're not going to develop the technologies and effectively the industry to remove that CO2 from the atmosphere.
Recent reports written by industrialists themselves confirm that it may be possible to reduce the costs of direct air capture to around $100 or even $50 per tonne, thus making the technology viable. In order to shift towards negative emissions and have an impact on the climate, direct air capture must be accompanied by a long-term storage system. The Hellisheidi geothermal power station supplies a third of Iceland's electricity. As part of the CarbFix research programme, Icelandic engineers, in partnership with the European Union, have developed a technology to inject the power plant's emissions directly into underground stone. The Swiss company Climeworks has set up a system that captures CO2 in the air and buries it.
This prototype here captures 50 tons of CO2 per year, which is maybe offsets 20 to 30 cars. With this, you can capture emissions from France or China or whatever, because the CO2 just mixes in the atmosphere around the globe, and you just install this wherever you have favorable conditions, storage conditions, and there you have it.
Using a filter and the energy supplied by the power plant, the CO2 is captured and then injected into subterranean layers of basalt more than 400 meters below ground.
So the CO2 comes from the plant. The CO2 is mixed with water. It goes into a steel pipe into the bedrock. The CO2 in this fluid, it is acid, or it creates acid, and this acid dissolves the rocks, and the rocks deliver cations into the solution, and they bind immediately with the CO2 to form another rocks. You can see here, you have these small bubbles. This is where we have space for the CO2 from the air to precipitate. And you can see these white spots. This is calcite, essentially just calcium carbonate. So it has calcium from the rock that it dissolved, and then CO2 is converted to solid rock. It stays there forever. It's not going to leak up to the surface and come back, so we have to capture it again and re-inject it. We just capture it, inject it, mineralize it, and it's gone.
Climeworks believes that this research project is a first step towards a world of negative emissions. The company has set itself the objective of capturing 1% of global CO2 emissions, but reversing the effects of 200 years' worth of burning fossil fuels is costly and takes time. This is why others are looking for solutions elsewhere, like in the oceans.
The way the ocean works is there's a lot of nutrients in the deep ocean, but nothing can do photosynthesis there because there's no light. At the surface of the ocean, there's a lot of light, but there's not much in the way of nutrients. If we put some additional nutrients in the surface that could allow organisms to photosynthesize, take the CO2, turn it into organic matter, and then that would sink into the deep ocean, pulling that carbon out of the atmosphere.
In British Columbia, the private organization Oceanos is developing a fertilization technique for oceans that can absorb a large quantity of carbon.
We have been working for the last 2 years on a specific ocean seeding compound that provides iron not in the form of rust, but in a bioavailable form. It's called iron 2. Iron is heavy, and iron sinks quickly. So what we did was we found a process that we can bind this iron with organic material like wood pulp, for instance, that floats or it sinks slower, basically. And it keeps that bioavailable iron available for a longer period of time. Instead of hours, it keeps it available for several days in the photic zone.
Will the supply of iron enable the phytoplankton to grow faster and absorb CO2 before sinking to the bottom of the oceans? In theory, each ton of iron added to the oceans could remove between 30,000 to 110,000 tons of CO2 from the atmosphere.
Ocean fertilization is probably the only carbon capture technology that's able to sequester a massive amount of CO2 at a very low cost. And as a by-effect, probably improving the marine ecosystem as well. We've developed a methodology where we can tag and measure if a fish grew as a result of our plankton bloom. And in the process of growing that plankton, it consumes CO2. And eventually these diatoms, these planktons will die, and a portion of that will sink to the bottom of the ocean and sequester the carbon there for long periods of time.
To date, a dozen experiments have taken place to test the impact of ocean fertilization on marine ecosystems. In 2009, the Indo-German program LOHAFEX gathered new data. Researchers poured more than 6 tons of iron into a 300 square kilometre stretch of ocean. This led to a twofold increase in phytoplankton in just 2 weeks. But the results of the experiment demonstrated that only a tiny amount of carbon actually reached the ocean floor.
We've done climate model simulations of the idea of ocean fertilization, and other groups have done so as well. And it seems like it basically works. It just doesn't work all that well. So we found that if you kind of fertilize the entire ocean and kept that going for 100 years, you might be storing each year something like 10% of what we're emitting each year. So the question is it worth kind of manipulating huge, vast areas of the ocean to solve 10% of the problem? Even in the most optimistic case, it only solves a small part of the problem.
Cette technique de fertilisation de l'océan, on ne connaît pas bien son efficacité, et puis elle a aussi sans doute un certain nombre d'inconvénients assez forts, puisqu'on va aller modifier les équilibres des écosystèmes océaniques. On va sans doute aller favoriser des espèces qui peuvent être invasives, qui peuvent modifier les équilibres entre espèces.
Oceanos hopes to carry out several ocean fertilization experiments in the years to come. But using human intervention to restore ecosystems and remove CO2 raises concerns among environmental organizations.
One of the things that a lot of people don't understand is that we only are going to apply 1 cup of iron to about the size of a soccer football field. And I think that whole idea of ocean fertilization, that we're pumping like massive amounts of chemicals in the water, is really not correct, and that's a misconception that the public has.
Hay, cientos de documentos que muestran que la fertilización oceánica ni siquiera está probado que pueda realmente absorber el carbono en forma permanente. Entonces está claro que es una tecnología que se desarrolló. Los que la han desarrollado más ha sido por razones comerciales, ¿no? Para ver si podían vender créditos de carbono, etc. Pero los científicos básicamente dicen de que es muy riesgosa para los sistemas oceánicos, marinos. Esto está reconocido en el Convenio de Diversidad Biológica, que tiene una moratoria contra la fertilización oceánica, y también está sobre todo reconocido en el Convenio de Londres, que tiene una decisión de prohibir la fertilización oceánica.
The oceans have absorbed a large proportion of global carbon emissions over the last few decades. According to recent studies, they show signs of reaching their saturation point in CO2, which is one of the leading causes of ocean acidification. We can't be sure that this fertilization will be enough to recover this process or provide an answer to this climatic emergency. Meanwhile, others are already coming up with ways of lowering the Earth's temperature.
So we have a problem that the atmosphere has gases that are trapping heat, and we'd like to take those gases out of the atmosphere and restore the balance of a healthy system. But taking the gases out of the atmosphere takes a long time. Nature takes a long time to bring them out, and artificial methods have to be created and distributed if we can bring them out. So if we need to address heat, then we may have to move more quickly than those options for bringing greenhouse gases out of the atmosphere. Solar geoengineering, or reflecting sunlight from the atmosphere, is today the only known way to reduce heat within a decade or 2.
Solar geoengineering just aims to provide symptomatic relief. It says, like, we're not really going to do much about the carbon dioxide in the atmosphere, but we're going to prevent the Earth from heating up by deflecting some sunlight away from the Earth.
The solar radiation that reaches our planet is not completely absorbed by the Earth's surface. some of the sun's rays are reflected and sent back into space through the atmosphere and land surfaces, a phenomenon commonly known as the albedo effect. On the 5th of November 1965, a scientific report sent to American President Lyndon B. Johnson was already warning of the dramatic consequences of rising CO2 levels in the atmosphere. It suggested for the first time increasing reflectivity by 1% in order to cool down the planet.
In 1998, we were in Aspen and we had a meeting about how to solve the climate problem. And most of the talks were about transforming the energy system or not cutting down forests. But there was one talk, somebody proposed putting some kind of shield to deflect sunlight away from the Earth.
Positioned at Lagrangian point 1 of neutral gravitation between the Earth and Sun, the idea of a space sunshade was proposed by astrophysicist Lowell Wood.
So I got back to my office, and we didn't have any money to work on this or anything, but the guy who had the next office over to me, he was running climate model. And we were really surprised at the outcome because it worked much better than we ever thought.
Shortly after the turn of the century, Ken Caldeira, one of the founding fathers of geoengineering, carried out the first simulations of solar geoengineering. He demonstrated that it was possible to limit global warming simply by diffusing the sunlight.
Some parts of the Earth system, like the coral reefs, the ice sheets, are facing potential collapse within 20 or 30 years, maybe. We want to have emergency options, then these kinds of options are the only thing that are known to work that quickly. And in marine cloud brightening, you could brighten clouds over 20% of the clouds of the ocean, maybe 3 or 4% of the ocean's surface, and possibly cool the entire planet by 2 degrees C.
Influencing the albedo of marine clouds to make them brighter was one of the 6 solutions chosen by the Australian government in 2018 to save the Great Barrier Reef, already a victim of global warming. In the USA, Marine Cloud Brightening Project researchers have developed the idea of an offshore floating device to enhance the reflectivity of marine clouds.
Clouds cover about 2/3 of the Earth's surface. So anything you can do to change the brightness of those clouds can change the amount of sunlight being reflected back to space. They already reflect a lot of sunlight back to space, so they act to cool, keep the planet actually cool. So marine cloud brightening is the idea that if we change the number of particles in those clouds, the number of droplets, the concentration of those droplets, we can actually make those clouds brighter. Each one of these little tracks is the effect of one single large container ship over the ocean. You can see that the brightness is increased where there are tracks showing that particles have been emitted by ships and are going into these clouds and making them brighter. But what we want to do is to take salt from the ocean, which is already a natural source of these cloud-forming particles, and we want to increase the number of those, and by doing that, deliberately increase the brightness of those clouds. And if we increase the brightness by a small amount, we can offset some of the warming due to the carbon dioxide.
So we might go from reflecting, let's say, 25% of the solar radiation to 50% of the solar radiation. That's a lot in terms of energy, but it's still allowing solar radiation through to the ocean.
Convinced by the potential of this method, a team of retired engineers from Silicon Valley have joined the project to help develop a system for diffusing particles.
If you go to the coast of California here, this is the clouds that we preferably would like to work with. So these clouds are not very reflective. So they look gray, they don't look white. So if you get more droplets and smaller droplets in it, they become white.
This is our nozzle in the hood here. It has 2 connections, one providing high compressed air, the bigger tube, and the smaller tube providing salt water. And they mix in the nozzle and come out as a spray. So to get it to work, Jack will turn on the compressed air first. And then I will turn on the pump to get the liquid.
Using this invention, engineers claim they are able to spray nanoparticles measuring between 0.2 and 0.3 micrometers, thus small enough to rise and remain suspended in the air. The team hopes to carry out a full-scale experiment within the next few years to act upon cloud reflectivity. Ultimately, the engineers are hoping to develop a spraying system capable of spraying more than 1,000 billion seawater particles per second.
It would be some time before we do a test that's big enough to measure whether we're brightening clouds. And in order to do that, you need a big patch of cloud and sky, like 100 kilometers by 100 kilometers, which is big for humans, but is small for the Earth. And you would go out in the remote ocean where the clouds are very clean and pristine, and you generate spray from the ocean seawater with 4 or 5 ships, and you traverse this area for several months.
All of this is very much in an exploratory and research mode. If I cool a piece of the climate system very strongly here, what does that do to a piece of the climate system over here? How does that propagate from here to here? We know this happens. We have examples of it on the west coast of the United States. There's this thing called El Nino. Every time the state of El Nino changes, the weather changes statistically.
By its very nature, the cooling is going to be regional. You know, it's going to be in places. We know that if you cool regions or warm them, that warming does spread out. So how much is the spreading and how does it then affect land areas, even though we don't seed those areas?
I personally think that it would be somewhat irresponsible for us to think about doing the solar climate engineering if we are not at the same time rapidly moving towards the idea of removing carbon dioxide from the atmosphere. So if you imagine you were trying to compensate for the warming due to CO2 by doing marine cloud brightening, every year there's more CO2 in the atmosphere, so every year we would have to make brighter and brighter clouds. Eventually you're going to run out of clouds to brighten. This is not going to work.
In 2006, Nobel Prize-winning chemist Paul Crutzen, famous for his work on the ozone layer, discussed the possibility of spraying aerosols into the stratosphere to reflect a portion of solar radiation and cool down the Earth.
Les aérosols, c'est tout simplement des particules en suspension dans l'atmosphère, soit dans la troposphère, la partie basse de l'atmosphère, soit dans la stratosphère, la partie plus haute de l'atmosphère.
In the stratosphere, located around 10 kilometers above the Earth's surface, particles move around horizontally rather than falling straight back down to Earth. On the 9th of June 1991, on the island of Luzon in the Philippines, volcano Pinatubo erupted after lying dormant for over 600 years. 5 days after the first eruption, a plume of ash and smoke rose 20 kilometers into the sky, releasing a large quantity of sulfur dioxide.
Volcanic eruption has a number of effects. Mainly, it can scatter sunlight and cool the surface of the Earth. Eruption in 1991 of Pinatubo put over 10 teragrams of sulfur dioxide and caused a significant amount of cooling globally, and it's been studied extensively for its impacts on the climate as well as the ozone layer.
The sulfate particles released by the volcano remained in the stratosphere for several years. A year after the eruption, temperatures fell by a few dozen degrees.
In the last 10 years, there have been a significant number of small and moderate eruptions that have also impacted the climate. We think that the forcing from the volcanoes offset about 30% of the warming from increased carbon dioxide between the years 2000 and 2015.
Observing the impact of volcanic eruptions on the climate has inspired scientists to develop the idea of spraying sulfur particles to cool down the planet.
NCAR was founded in 1960, and one big part that we do is develop a climate model. And in this way, we can simulate, for example, the past and the present climate, and we can also simulate the future climate. We cannot really test geoengineering in the way that it would be applied, because that would mean we would have to inject large amount of gases or aerosols in the stratosphere, but we don't know what it does, and we don't know what the impacts are. So our best tool is really right now to use climate models or large Earth system models to simulate the effect of geoengineering. Hiya. The first experiments were that we basically dimmed the sun. We turned off the solar constant, and in that way, basically you can see what is happening to the cooling. Can we actually cool the surface and counteract greenhouse gases and the warming when you just turn down a little bit the sun? And then people started to use more complicated models, and they did something similar what volcanoes did. They injected in the tropics.
In this example, you can see the spread of a cloud of aerosols from a single source over a 2-year period. The particles move around horizontally within the stratosphere and end up covering a large part of the Earth's surface.
We explored how you can inject gases at a certain location to then change their aerosol so you would actually control the movement and get the cooling you want to achieve.
Controlling the injection and spread of aerosols within the stratosphere to reach an optimal coverage is one of the challenges currently faced by geoengineering.
We inject the aerosols here, right, in 15 north, and you can nicely see how the aerosols cover this one latitude while we are injecting very close to the tropics, and then if we continue in the next year to inject in the other hemisphere in 15 north, you can see also how quickly those aerosols move around the globe and then slowly also cover the other part of the hemisphere. And in this way, we eventually can reach a global coverage with these aerosols and reach global dimming.
Injecting sulfur dioxide, calcium carbonate, or even diamonds. Many different types of particles are being looked into. Engineers believe this can be done using aeroplanes or pipes hanging from balloons.
Why wouldn't you want to just do it tomorrow if it's so wonderful? We're not really sure what the side effects will be. I mean, the Earth system is an incredibly complicated system, and our models are very complicated, but our models are just a very crude representation of all the rich detail of reality. And so we can be sure anytime you interfere in a complicated system that something's going to happen that you don't expect. And so from an environmental point of view, the thing that I'm most concerned about are unintended consequences. There could be long-term effects on ecosystems that we don't know about.
We see regions that show more droughts, and we see regions that show an increase in precipitation, which is, however, much smaller than what you would see with just global warming.
If they were to be deployed in the near future, sulfate aerosols could alter the chemical structure of the stratosphere and therefore slow down the progress made to rebuild the ozone layer. Depending on the size of particles used, the brightness and color of the sky could also change. We also know very little about the toxicity of these aerosols once they fall back down to Earth. Several million tons of particles could maintain or even lower the Earth's temperature, even if greenhouse gas emissions were to double.
The risk is the longer we apply geoengineering, the more we inject, the more dependent we are on geoengineering to keep doing this. And the most important part of applying geoengineering to me is that we at the same time reduce greenhouse gases, that eventually we can again stop geoengineering.
People start thinking like, oh, there's this cheap and easy technical fix. All we have to do is have some planes distributing some particles in the stratosphere. So why do we have to bother with all these wind turbines and solar and this whole transformation of our energy system? That's the bigger threat, because if we continue emitting greenhouse gases, then you have to ramp up the amount of aerosols you need, and the end game of that is pretty ugly because you end up with an atmosphere that's rich in greenhouse gases and a thick layer of aerosols. And if you ever turn off those aerosols, all that masked warming would come back, and that's not a pretty picture.
It's the termination effect. If after 50 years of solar geoengineering we stop releasing aerosols into the stratosphere, the temperature will sharply rise by more than 2 degrees in less than 10 years.
En quelques années, disons 10-15 ans, on rattrape tout le réchauffement qu'on a finalement masqué, qu'on a cherché à éviter pendant la période où on a maintenu cette injection d'aérosols stratosphériques. Et donc qui dit réchauffement rapide dit aussi une difficulté beaucoup plus grande à s'adapter au réchauffement climatique, que ce soit pour les sociétés mais aussi pour les écosystèmes naturels.
Little by little, geoengineering is now securing its place at the discussion table regarding global warming. A small group of researchers, mainly in North America, Europe and China, are starting to study it seriously.
At this point, solar geoengineering is still just an idea.
David Keith is the head of the Geoengineering Research Program at Harvard, one of the biggest research centers in the field.
Last year, we've seen hundreds of scientific papers. We've developed specific plans for experiments, something called the Stratosphere Controlled Perturbation Experiment, SCOPEX. That experiment would tell us a great deal about how this technology could work, what its risks are, could surprise us in ways that it wouldn't work. Because one thing research may find is this doesn't work very well. The whole point of research is to reduce our ignorance. But that test would not itself be changing the climate. In the SCOPEX test, we would put less than 10 grams of sulfur in the stratosphere. That's what you put in 2 or 3 minutes of flight of a regular commercial airliner flying to Europe. You cannot uninvent this technology. Our children will be faced with decisions about climate change and about solar geoengineering, whatever we believe today. If we choose not to have a research program, we give them the gift of ignorance. And they will make decisions on that basis.
Research into geoengineering has come at a turning point where experimentation is becoming imperative. Should we prevent these experiments or regulate them?
Going out in the open, doing outdoor field trials is a red line. It's a political red line that will sort of normalize the idea of doing geoengineering interventions. And the bigger these experimentations get, the more credibility that is being lent to them. Outdoor experimentation should not go ahead before we've had an international conversation about this topic.
Controlling the climatic thermostat will require new legal provisions, international agreements and treaties, thus providing a framework for future experimentation.
If you would ask me today to vote whether to start solar geoengineering tomorrow or next year, or to never ever do it, frankly, I would vote for never ever doing it, because we simply don't know enough. Solar geoengineering reverses most of the problems we know about, most of the characteristics of climate change on the one hand or climate policy on the other, right? That it is slow, it is expensive, it's global, it takes incentives to put people together. Right? Paris Agreement was all about getting countries to agree to do more than they otherwise would. Well, all these properties reverse when it comes to solar geoengineering. It's quick, it's cheap. The quantities involved of aerosols that need to be lofted into the stratosphere are relatively small. Less than 10 planes flying, right, year-round, if you will, delivering material into the stratosphere. And it is imperfect. It is not a solution to climate change. The real problem is stopping people, stopping countries, stopping overall action that might be too quick, too fast, and not done in an appropriate way.
Costing much less than an actual policy to reduce CO2 emissions, solar geoengineering, and particularly the technique of stratospheric aerosols injection, would be accessible to any country.
at what point can this get out of hand? Like how can you prevent other actors, powerful states, military actors, even corporate actors to use that technology in their interests? Patents have already been registered on certain, on the various geoengineering technologies, on certain, types of the hardware or certain processes, certain aspects of that technology.
There is basically no funding for experiments. We have some people that are doing modeling studies, including us and the stratospheric aerosol people, but nobody really has money to do serious testing. And the only money that we have to even start thinking about serious testing is all coming from private sources. So there is a broader issue for society about whether or not it's important to have these experiments publicly funded. Because the question of who owns, suppose you have a company that goes out and pays to do this testing and says, I now own the property, the intellectual property to make this happen.
Geoengineering research is, for the most part, funded by private donors. Bill Gates has invested millions of dollars into funding this research. A study in 2014 identified 143 patents relating to geoengineering technologies, primarily in the field of carbon dioxide removal. In Silicon Valley, the company ICE 911 has developed a controversial geoengineering technique.
I started ICE 911 in 2006 when I saw the Al Gore Inconvenient Truth movie. One of the things in the film that really stood out for me was the ice albedo feedback effect. When the summer sun is shining on this now darker ice and ocean, more solar energy is being absorbed rather than reflected.
To restore the reflective properties of ice, ICE 911 is developing a protective material that can be scattered across sheets of ice.
So these are a material that are fundamentally like sand, but it has an inert gas bubble in the middle of it and a thin shell of silica around it. And when we put it in water, it'll float, can then make a profound protection of ice and snow underneath because it makes it reflective, bright enough that you're reflecting off the sunlight.
After several tests in Alaska, the company, funded by private donors, is waiting for permission to test its geoengineering process on a greater scale. This time in the Beaufort Gyre in the middle of the Arctic.
We just got news this winter that the Arctic formed virtually no new ice, and the amount of ice that is in the Arctic in the summer determines how stable our climate is, how much cooling we have, how much solar radiation is reflected back to space. So you want as much ice there as possible in the summer. And in order to do that, you need to form the most in the winter. And what's one of the ways you can aid that process? You put this material on top, so you cool that surface layer and let more build from underneath. Look how much brighter the material is than the surrounding area.
And the size of deployment we're thinking of are things on the order of 0.5% of the area of the Arctic, in strategic areas. That could make a very large impact. And we're showing in the climate modeling the ability to rebuild not just ice area, which happens in some sense every winter. You rebuild thin ice all over the Arctic, but very importantly, ice volume. And it's that ice thickness that allows you to build back to having a high reflectivity ice again. High albedo ice is what the experts call it. That's what we're after, trying to reboot that process.
ICE 911 hopes to ultimately acquire between 3 to 6 container ships to help scatter these glass microbeads and, in its own words, save the Arctic. The idea that we may be confronted with a climate emergency in the next few years is spreading, and the public debate on geoengineering has only just begun.
If I was to ask you, how much would it cost to build a large gigawatt power nuclear power plant in Germany? The answer is, well, you can't. And the reason you can't is not because the Germans don't have the technical ability and not because they they don't have the money, it's because they don't have the political will. They've made a decision they don't want to do it. So for a technology to work, it's not about can it work just physically, it's also about whether it can work socially and politically as well. The question is, can it be done in a way that would be socially acceptable, politically acceptable? How would it actually happen? Would you have one country deploying it and other countries just going along with it? Or would you have an international agreement, and how would it be structured? Lots of questions about, well, how do you maintain this system? If you're going to have such a system, what rate do you set it at? Do you say you want half a degree of warming, 1 degree, 1.5 degrees? Who decides?
No es cierto que esté probado en ninguna parte que no alcance con reducir y con otra cantidad de alternativas. De hecho, por ejemplo, el Panel Intergubernamental de Cambio Climático, el IPCC, está estudiando diferentes opciones donde incluye geoingeniería, pero otras propuestas no las incluye, como por ejemplo masificar apoyando la agroecología campesina o la agricultura campesina, todo lo que es recuperar los ecosistemas muy degradados, como por ejemplo los humedales, como por ejemplo, bueno, muchos bosques y eso, en donde eso le daría mucho trabajo y bienestar a las comunidades que viven ahí. Entonces no es solo un tema de absorber carbono, es múltiple. Todas esas opciones casi no están siendo estudiadas. Entonces, yo entiendo que hay investigadores que ellos en su manera de pensar pueden ser, digamos, pueden ser hasta bien intencionados, es decir, vamos a ver qué sucede con esta tecnología, pero el efecto en el mundo real que vivimos es terrible, porque eso quiere decir que otra vez se vuelve a crear una injusticia entre los que están más afectados del cambio climático en el sur y los que tienen los recursos para investigar en el norte.
The inertia and inability of societies to act on the causes of global warming are pushing others towards the idea of climate control. But is geoengineering, man's final step towards controlling nature, really a desirable solution? Is it too late for a global energy transition? While the window for keeping global warming below 2 degrees is rapidly closing, the time to act is now or never.